Hello and welcome to our section 18.3 video lecture on T lymphocytes or T cells and cellular immunity. So when we talk about cellular immunity, we're talking about targeting and getting rid of any intracellular pathogens through the action of our T cells. And they really play a big role in orchestrating and organizing our overall adaptive immune system response. And we're going to see the interplay of our humoral immune system in the next section. But for now, we'll focus on cellular immunity, and we want to achieve these learning objectives to be able to describe the process of T cell maturation and thymic selection, and explain the genetic events that lead to diversity of T cell receptors. We want to compare and contrast the various classes and subtypes of our T cells in terms of activation and function, and explain the mechanism by which superantigens affect unregulated T cell activation. So first, let's talk through the process of how we produce our T cells and how they mature. So we already kind of know the beginning portion of this through the process of hematopoiesis. We're going to start off with our multipotent hematopoietic stem cells, or HSCs, in the bone marrow, and then through the process of that lymphoid lineage, we're going to take our lymphoid stem cells and turn them into immature lymphocytes known as lymphoblasts. Now, at that point, we can enter the bloodstream and travel to the thymus. Remember, T cells are called that because of the T in thymus, and that's where they're going to mature. And now we change their name from lymphoblasts to thymocytes. And within the thymus, they're going to go through a process of thymic selection, which is also known as our positive and negative selection process. So we see up here our immature thymocyte, and we're going to have all these different receptors on here. Eventually, we will choose which ones will stay, but we absolutely want our T cell receptors to stay and for them to be effective, right? So we go through a process of negative selection in order to get rid of any thymocytes that are not going to respond properly to our body cells. So we essentially tell these cells that have defective T cell receptors to go through apoptosis so that they don't interact with our HLA or MHC class 1 molecules, and we get rid of them. We also go through a process called positive selection, in which we see that our cell receptors are binding with self HLA molecules or MHC class 1 molecules appropriately. So because they're interacting appropriately, we allow them to stick around. They don't go through a process of apoptosis, and they get signaling to become either a mature CD4 or helper T cell, or CD8, a killer T cell. Now, through the maturation process, we are able to achieve something known as central tolerance, which means that we're preventing these self-reacting T cells from entering the bloodstream and possibly causing an autoimmune disease. Now, some of those self-reactive T cells that are able to make it through somehow escape the thymus, and we are able to use mechanisms of anergy, which is going to be our state of non-responsiveness to antigen stimulation. And we use inhibition of self-reactive T cells by the use of our regulatory T cells to achieve what's known as peripheral tolerance. So essentially, they are not receiving a co-stimulatory signal. And by that way, our regulatory T cells are able to inhibit activation and function of those self-reactive T cells by secreting anti-inflammatory cytokines. So now that we've achieved both central and peripheral tolerance, our cells are mature, naive T cells. And we say naive because they have not interacted with an antigen that has been presented by an antigen-presenting cell and activated it. So what happens is, through this process, we eliminate about 98% of our thymocytes, and the remaining 2% that exit the thymus and are now mature naive T cells are going to end up in areas such as our lymph nodes, the spleen, our tonsils, and they just hang around in order to become activated through presentation of a specific antigen from a pathogen by our antigen presenting cells. And once they're activated, they can get to work. So let's see what the different classes of T cells are. We've got our helper T cells that I've mentioned, regulatory T cells, and our cytotoxic or killer T cells. And these are identified really by those CD molecules. And CD stands for cluster of differentiation. And they are just surface glycoproteins. And like I said, they're kind of an ID. So you could see that our CD4 cells are on our helper T cells, CD8 is on our cytotoxic T cells, and CD4 and CD25 are found on our T regulatory cells. So our goal of our CD4 cells is to be activated by an APC with an MHC class II molecule, whereas our cytotoxic T cells, they're able to recognize antigens presented by MHC1 by our APCs, or it could just be a nucleated cell. Now let's talk about what happens when they become activated. Our helper T cells will work to activate and direct the functions of both our humoral and cellular immunity, and their job is to really enhance the pathogen killing functions of our macrophages and those NK cells. So it does also jump in a little bit into our innate immune system. And then our regulatory T cells, remember they had that role in the peripheral tolerance. So I always think of these cells as the ones that have the stop sign to stop the immune attack against our own body cells, or from our immune cells overreacting, trying to kill a pathogen and causing harm to our own body cells is really the way to think about it. All right, and then our cytotoxic or killer T cells, they recognize, target, and destroy the cells that have those intracellular pathogens within them. So we have to have some specific binding taking place in order for all of this to happen. So our T cell receptors will play an important role in that. And they are also going to have an antigen binding site that is epitope specific. So this area is going to be the variable region that contains that. And then we also have a constant region here that is bound together with a disulfide bond. Now this TCR is going to come from the same family as our IgD and IgM, so they do have similarities, as I'm sure you can see here, and therefore will have similar processes. So we do have that genetic rearrangement that could take place over here to make sure that we have unique epitope binding TCRs. Let's walk through how we're going to activate and differentiate the helper T cells. So in order to achieve activation, we have our T cell here that is going to be presented with a MHC class II molecule with that foreign antigen presented on it, and that is binding to our TCR. So we get TCR recognition of that foreign epitope or antigen there. Then we have an interaction between our CD4 molecule that again is on our T cell with the MHC class II molecule as well, but notice it's not at the antigen presenting site. It's a little off on the side. So we need those two things in order for our helper T cell to become activated. Then what happens is our APC and the T cell are going to secrete cytokines, chemical messengers that are going to activate the T cell. And then basically that allows our T cell to proliferate and produce clonal helper T cells that can differentiate into the subtypes with its different functions. So we've got a table listed here, but let's talk about their functions on the next slide. So we've got our effector helper T cells first. These are short-lived and they perform a lot of different functions in our immediate immune response. Our memory helper T cells are going to be long-lived, as we want them to be to remember, right? They're going to remember that specific antigen or epitope that we were presented with. And so the second time we become infected, we're able to form a rapid and strong immune response. Then we have our Th1 cells. These are going to secrete cytokines to stimulate other cells in our immune system. So what we mean by that is stimulating those killer T cells, enhancing the killing of infected cells, and promote differentiation into memory killer T cells for that secondary response. We can also stimulate our macrophages, neutrophils, and K cells to become more effective. Now with our NH2 cells, that's going to help to orchestrate the humoral response. So they're really working with our B cells, and we do this by secretion of cytokines and tell the B cells to differentiate and create antibodies so that we can switch the antibodies from IgM, IgG, IgA, IgE as we need them. And then we've got our Th17 cells, which is the body's defense against chronic mucocutaneous infections. And people who don't have these cells in their mucosa may be more susceptible to things like bacteremia and GI infections. And this tend to be people who are infected with HIV. Now that we've talked about activation and differentiation of our helper T cells, we need to talk about our cytotoxic or T cells and the process that takes place there. So it's a little bit similar, but there are some differences. And one of those differences is that we need to use a MHC class 1 molecule here instead of MHC class 2. And we've also got CD8. I'm losing my mouse here, sorry. There we go, our CD8 molecule instead of CD4. So we have that co-recognition taking place of the foreign epitope or antigen on the MHC class 1 molecule. And that, of course, is attaching to our T cell receptor. And then we've got the CD8 molecule attaching to the outside of the class 1 molecule. Once we get that co-recognition, we can release the cytokines by the APC and the killer T cell to activate clonal proliferation and differentiation into our effector cytotoxic T cells or memory cells. And so as we have this binding taking place, we are going to release perforins and granzymes that are going to work to destroy the infected cell. Remember that the perforins are going to be a protein that creates a pore in our target cell here, and then the granzymes are going to move in through those pores, and they are proteases that are going to induce apoptosis or programmed cell suicide. And what is really special about this is that they are able to create this cell death without releasing the pathogens inside to infect their neighboring cells. Okay, last topic we're going to talk about are our super antigens. What we mean by that is it is a protein produced by some bacteria and viruses that are going to cause an excessive immune response. So you can see in this image down here that we have no recognition really taking place here, so there's no immune response. And then over here, we can see that there is a super antigen that is attaching to the outside here that is able to bridge and cause this binding between the MHC molecule and the T cell receptor that then causes an excessive release of these cytokines and activates other T cells for excessive inflammation to take place. Now we have some known bacterial superantigens, and you may have heard of some of these, such as toxic shock syndrome toxin or TSST, staphylococcal enterotoxins, streptococcal pyrogenic toxins, streptococcal superantigen, and streptococcal mitogenic exotoxin. And for viruses, we know that certain viruses are able to produce superantigens, such as the Epstein-Barr virus and the cytomegalovirus. And when these cytokines are released, it is known as a cytokine storm. So we have excessive release, and it stimulates, like we said, that inflammatory response, which could be really dangerous because it leads to drops in blood pressure, which can then lead to shock, leading to multi-organ failure and potentially death. Now let's revisit our clinical focus on Olivia. She's having a strong immune reaction that is systemic and also seems to be experiencing extreme neck pain. So the physician decides to order a CBC, blood culture, and lumbar puncture. When the results come back, they see that the CSF appears cloudy and send it for gram stain assessment. We also see that the glucose levels are low and the white blood cell count is extremely high within the CSF. And when we get the CBC, we see elevated white blood cells and a high neutrophil percentage. So based on these results, do you have a preliminary diagnosis? And what is recommended for treatment based on your preliminary diagnosis?